Hi, welcome to Analysis, Design, and Simulation of a Flyback Part 3. In the second video, I simulated the transformer by using a coupled inductor model. Okay, so I'm going to introduce another model which is equivalent, and we're going to simulate using the ideal transformer model. Okay, you can use either one. Let me just recap what the coupled inductor model was. Basically, you have an inductor primary, you have a secondary inductor, and for a flyback, we need to make sure that the dots are reversed or out of phase. Once you have that, you need a K element. Usually it looks something like this. And in the K element, you define which inductors will be coupled. And typically the line will look something like this. It'll say L1, which is the primary, and then L2, which is the secondary, and then you have this number here. That's typically that's referenced as K, or as the coupling coefficient. Coupling coefficient. Okay. So basically, when you put a 1 on 1 means 100%. 100% of what? Well, what it means is that when you power or energize the primary, that as soon as you turn off the MOSFET, all the flux lines, 100%, will be coupled directly to your secondary. Okay. Now, in real case or real world, you don't have this. In real world, you typically will have in the 90s. In the example that I'll be using in other simulations after this video, I will be using a K of 0.999. That means that 99.9% of the flux lines are coupled to the secondary. Okay, that means that only 0.1% will not be coupled. Okay, and that 1% means that it introduces a leakage or a series inductor that's not coupled to these two. Okay, but right now I won't get into this. In the next video I'll get into that. Okay, so you've already seen this and you've seen that it works fairly well. Okay, but the main goal of this video is to introduce the ideal transformer model, which is another way of modeling a transformer. In your simulator, SPICE simulator, whether it's PSPICE, LT, Top SPICE, you should have a SPICE that's an ideal transformer. Okay, and within the transformer, you don't have to define inductances or anything. Typically, all you define is N. What is N? Well, we know that it's the turns ratio. And as I have it up here, let me rewrite it. And the definition of turns ratio is really L of the secondary, well, the square root of the secondary over the primary. So that's the definition. And as a matter of fact, On when I do my simulation, if you solve for S, you end up with L secondary is equal to LP times N squared. And that's why on my spice, I like to use that convention for the coupled inductor. But anyway, I digressed it a little bit. Let me continue with this one. Now, you have to use an ideal transformer. Typically, you'll have a connection there, 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 and so forth. Let me go ahead and erase this. Okay, and then what you do is you put or you add an inductor across the primary of the transformer. Okay, so this inductor will represent the magnetization current, or the primary actually. Okay, so you're gonna have current going through here. So by defining that, putting an inductor and using an ideal transformer, you can actually model a transformer. Okay, and like I said, you have to define N. Now the other thing that you need to keep track is typically on the ideal transformer, the phases will be in phase. Now we know for flyback they have to be out of phase. So when you make your connection, typically the diode goes up here if you use out of phase, but since they're in phase, or at least the symbols are in phase, you have to put the ground here, and then here that's where you put your diode and cap and resistor. Okay, so let's simulate it. Simulate or spice it. See how well it works. Okay, so I'll zoom out, and what I did is, this is the coupled inductor model that you're seeing in video 2, and like I said, it's L1, L2, and then coupling coefficient 1, and I have the curly brackets LP. Okay, the curly bracket means that it's a parameter, so I define it here as LP. Okay, and remember on here I had mentioned that if you solve for LS, well, LS is really LP times N squared. Well, I make use of that here. For the secondary, which is L2, I define it as NR times NR times LP. So again, it's a curly bracket, means I have to define it. LP is already defined here. All I need is to define NR. I have it defined here. So I have my inductor model defined. My K is defined, L1, L2, and 1. And of course I have other parameters that help me set the 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 pulse width and the period. Here I have an initial value of 0, a pulse value of 12 volts, time rise and fall time of 100 nanoseconds, and then for the pulse width I have the curly bracket, which is a parameter, and I define duty cycles divided by free curly brackets, and then the period as the reciprocal of freak. And of course the number of periods, I went ahead and set it to 1 gig. So once I have those parameters within the curly brackets, they're defined here. Free is 100 kilohertz, and then duty cycle is 50%, which is 0.5. Okay. Another thing that I did is I defined curly brackets for the load resistor. My load resistor is 24 volts. What's neat about using the curly bracket is, if you notice, I have our load here, and I also have it right here. So instead of coming in here, let's say if I want to keep these two circuits identical and I want to change the load to, let's say, 100 on both circuits, well, I would have to double click on this, change this to 100, and then I have to do the same thing here. But because they're global, I can have maybe 2 or 3 of these defined within my circuit, and instead of changing all of those, all I have to define is just one, and it changes all of them. So that's the advantage of using parameters, that you can do changes like that globally. Okay. Here we have, let me focus a little bit, at least on the transformer. Here's my ideal transformer. Again, notice that you have the phase up on top, and then I define the turns ratio. In this case, it's NR, okay, turns ratio, number of turns, and I have it defined as 0.5, okay. And then right here I have my inductor. Uh, where the dot is, it really doesn't matter. I can flip it. It really doesn't change the simulation, as long as that you know that you have to connect your ground up on top if these are in phase, and then you do your connection on the undotted area. And again, you can see I have my diode, capacitor, R load, basically the same identical circuit that I have on top, I have on the bottom. So the top one has the coupled inductor, and this one is using the ideal transformer. Okay. Uh, the only other thing that's different is have here out for the coupled inductor, and I have V, or actually out 2 for the ideal transformer. So basically anything that has 2 is associated with the ideal transformer. Anything with that is not, doesn't have a number, is the coupled inductor. Now let me go ahead and run. I'm going to go ahead and run it. See whether they're the same, or at least to prove that they're the same. Okay, here we have the results. Okay, if you can tell right here, it says V out and V out 2. So basically the voltage is identical. Okay, and here I'm plotting the voltage on the drain, and other than maybe a little excursion here and there, minor ones, if I zoom in, they're basically on top of each other. Okay, the only place that you do see a difference, and it's a good difference, okay, and let me explain this. See, these little spikes are just artifacts, so those are not real. Those are spice uh, artifacts, I guess you can call it. Now let me concentrate on this and try to explain this a little bit. And let me turn these off. I want to concentrate on these for a while, or at least explain. Uh, Let me do something else. Let me go ahead and see if I can. copy. See if it does what I want to do. Okay. Yes. Okay. Here, basically, this plot is the current going through the primary, and I'm showing the current of the primary of the coupled inductor, and also the current going through the ideal inductor, actually this L3. Okay, and as you can tell, they look a little bit different. Okay, so you notice this blue, and let me remind that the blue one is the coupled inductor, and the red one is the ideal transformer model. Okay, and what's neat about the transformer model, it's a little bit more intuitive. Now keep in mind that this transformer or this flyback that I'm designing is supposed to be a discontinuous transformer. Okay, and discontinuous means that all the flux in the transformer is used up. In other words, it goes to zero. Okay, that implies that the current in the primary has to go to zero. Okay, in other words, you stored all this energy in the primary during the time on, and then during the time off, you have to dissipate everything, or at least that's the idea. Okay, well, when you look in here, this is the coupled inductor model. This is the current in the primary, and if you notice during time on, it ramps up, and then it looks like the current goes to zero. Okay, so you would think, or at least when I first started studying power supplies, I saw, oh well, there's no current in the primary, it's zero, so it must be in discontinuous. Okay, but in reality, it's not. If you notice, if you look at the red is the transformer model. Okay, in other words, this current is this current, the current going through this inductor that I added to the transformer, ideal transformer. Okay, so what it's telling me here is at startup, you during the upper slope, the inductor is being charged. That means the MOSFET is on, and then the downward slope, the energy is being released, meaning that the MOSFET is off. Okay, but if you notice, it's got current. It did not release all of the current. Okay, and if you notice, it keeps going up, up, up. Okay, and it doesn't come back to zero until about 80 something microseconds. So during this time, we're actually operating in what is called continuous conduction mode. In other words, during this time, the energy is still it still has energy, or it still has current in the primary. So when you look at this curve, it doesn't you don't see that. It's not as intuitive using the coupled inductor model. But if you use the ideal model, then it becomes more intuitive, because you can see, oh well, it still has current. So during this time is continuous. Then once it goes to zero, then that's when it goes into what we call discontinuous. So basically, continuous, and then right after that, it's reached steady state. It's operating in the discontinuous mode. So this is a powerful model to use. It makes it a little bit more intuitive, and in many ways it's a little bit more simpler, because you don't have to define as many parts. All you have to do is put an LP, an NR, and you're done. Here I had to do LP, and then I had to define the secondary, and then I had to define K. So between both of these, this is a much simpler model, okay? And I'll let you in a little secret. This model runs a little longer than this. In other words, this model is faster. So if you have a circuit that you're going to simulate for a long time or is complicated, this is the model that I would use. Okay. So anyway, that's the introduction of the model. You can use either one. You may feel more comfortable going this way with the couple inductor, or you may have a better feel for using the transformer model. Either one is equivalent. Now on the next video, I will show you how to introduce leakage into both of these models, and then hopefully we'll see the effects